This is my lab 4 on the macroscopic view of DC and RC circuits. So the problem here is that I need to measure the conventional current and potential difference in various circuit setups, observe the behavior of these circuits, and compare a calculated time constant to a known one. The results overall, we see that the loop rule is proven. Capacitor's discharge time depends on the amount of resistance, and the calculated time constant is close to the known value. The sections that we'll go over in this lab include the theoretical model, the governing physics principles, and the relation between those principles and model and the outcomes in data and measurements. So the models used in this lab, we have two. First is the series circuit, which was used to find potential differences, current, and resistance within that circuit. And it was a setup of two batteries, two resistors, and two ammeters. And then for the other half of the lab was an RC circuit, which was used to observe how a capacitor charges and calculate an RC value. And it consisted of one light bulb, one battery, and one capacitor. So the principles in this lab include the conservation of energy, which says that in a closed loop, the total voltage equals the sum of all voltage drops in the same loop, or Kirchhoff's second law. And also current conservation, which is the sum of the currents flowing into a junction is equal to the sum flowing out of that junction, or charge conservation steady state. And then applying these principles, these laws allow us to check the reasonableness of our results. And this lab consists of a lot of in and out measurements, which we'll see, which should ultimately be equal to each other when following these laws. So with the first part, we have charge and energy conservation in series circuits. So I1 was equal to I2, which was 0.02 amps. And this read the same when the ammeter was inserted backwards. And then the voltmeter read positive or negative 3 volts, depending on the position it was placed in, whether at position 1 or 2. And when the voltmeter was placed in the circuit, the ammeter read 0 amps because it became an open circuit with a voltmeter placed in it. And then here you can see the values for each of these locations in the circuit. And overall, they add up to 0, and the V total is 3, the R total is 147, and the I total would be 3 divided by 147, or 0.0204. Here's a graph of the potential differences. So between C and D, it goes down by 0.959, and between E and F, it goes down by 2.041, as seen in this slide, and then it goes down to 0. And the resistance of several circuit elements, the 47 ohm resistor was 0.00652, the 100 ohm resistor was 0.0139, and both the wire and ammeter had a resistance of 0. So for the second half of the lab, we had RC circuits, and when the circuits were set up, there would be light for a little bit until the capacitor fully discharged, and the same thing happened after removing the battery from the circuit. And the current was able to flow when the capacitor began to discharge. And then down here you can see the times it took to charge and discharge for a 10 ohm and 20 ohm bulb, and of course for the 20 ohm bulb it was slightly longer for both charging and discharging. And then the last part of the lab was time-dependent voltage across a discharging capacitor. So here's a graph of time versus the natural log of voltage over initial voltage, which gives us a slope of -1 over RC. So we can calculate RC, which was 6.54 seconds, and the expected value in the simulator was 6, so that's pretty close. And questions. What if I used an actual ammeter? What is different about a real one, and how would it have affected my circuits? So the currents would be lower because a real ammeter would have way more resistance than the ideal one in the simulator. And what if I used a real battery to charge a real capacitor with no resistor in the circuit? How quickly does the ideal model reach full charge? Would that happen in real life? So the capacitor would not reach full charge instantly as shown in the ideal model of the simulator. And in conclusion, we can prove complex physics principles through fairly simple experimental setups in a simulator, like Kirchhoff's laws, loop rule, energy conservation. And the resulting measurements were all reasonable because they checked out with the aforementioned laws, and currents and resistance go hand in hand.